August 31, 1943, Task Force 15 over Marcus Island. F6F-3 Hellcats roll from Essex-class decks. New fighter direction lights the scope. The goal is blunt. Test America's 2,000 horsepower answer to zero dominance and keep the fleet alive. Essex, Yorktown, and Independence are the striking core, pushing the fast carrier doctrine west. Flight Petty Officer Toshiyuki Sueda pressed his Mitsubishi A6M Zero into a climbing turn as unidentified American fighters approached from the northeast at 14,000 feet. For 2 years, Imperial Navy pilots like Sueda had ruled Pacific skies with tactical superiority that often proved decisive. The agile Zero-Sen had outclassed many Allied fighters that dared challenge it, from obsolete Brewster Buffaloes to the rugged but outmatched Grumman F4F Wildcats. Now, as morning sunlight glinted off unfamiliar American aircraft approaching Marcus Island, Sueda was about to discover that technological supremacy had shifted decisively against Japan. Lieutenant Richard Loesch of Fighting Squadron 5 adjusted his throttle as his Grumman F6F-3 Hellcat closed toward the Japanese formation with the steady authority of overwhelming power. The new fighter beneath him represented an 18-month development program that had transformed American naval aviation from defensive parity to offensive dominance. Where the F4F Wildcat had struggled against zero performance advantages, the F6F Hellcat outclassed the Japanese fighter in most combat-relevant categories, especially at higher speeds and medium to high altitudes, while ceding advantages in range and low-speed maneuverability. The Pratt & Whitney R-2800-10 double Wasp radial engine in Loesch's Hellcat produced 2,000 horsepower, roughly 3/4 more power than the Nakajima Sakare engine that drove Sueda's Zero to its maximum performance. Warrant Officer Sueda banked his Zero into position for what he expected would be another routine interception of inferior American aircraft. Japanese intelligence reports had identified new enemy fighters operating from American carriers, but tactical assessments suggested these represented minor improvements over existing designs rather than fundamental advances in combat capability. The approaching aircraft bore superficial resemblance to the familiar Wildcat profile, leading Sueda to assume he was engaging upgraded versions of fighters that Japanese pilots had consistently defeated throughout 1942 and early 1943. This tactical miscalculation would prove representative of broader Japanese failures to recognize the magnitude of American technological advancement. Grumman Aircraft Engineering Corporation's design philosophy for the F6F emphasized pilot survivability and mechanical reliability over the pure performance optimization that characterized Japanese fighter development. Where the Zero achieved exceptional maneuverability through minimal weight and structural optimization, the Hellcat incorporated cockpit armor, self-sealing fuel tanks, and redundant control systems that allowed continued operation despite battle damage. Chief Test Pilot Corwin Meyer had described the Hellcat as designed to be flown by 200-hour farm boys, reflecting an approach to fighter design that prioritized operational simplicity and pilot protection over aerodynamic refinement. The engagement that followed would establish patterns that would define air combat for the remainder of the Pacific War. Loesch's F6F accelerated toward the Japanese formation with speed and climb performance that exceeded Zero capabilities above 14,000 feet altitude. The Hellcat's maximum speed of about 375 to 380 miles per hour translated into a roughly 30-50 mile per hour advantage over the Zero at combat altitudes, depending on model and conditions, while its superior power-to-weight ratio enabled sustained high-speed maneuvering that the Japanese fighter could not match. When Sueda attempted to evade through the tight turning maneuvers that had proved effective against earlier American fighters, Loesch's Hellcat remained in firing position through superior roll and diving performance at higher speeds. 6 Browning M250 caliber machine guns in the Hellcat's wings delivered concentrated firepower that devastated the Zero's unprotected structure with catastrophic effectiveness. Each gun carried 400 rounds of ammunition, providing sustained firing capability that far exceeded the Zero's mixed armament of 20mm cannon, typically 60 to 100 rounds per gun, depending on model, and 77mm machine guns with approximately 500 rounds. The weight of fire delivered by 650 caliber weapons proved immediately decisive against Japanese aircraft that had sacrificed armor protection for maneuverability and range. Sueda's Zero disintegrated under a 2-second burst that would have caused manageable damage to the heavily protected Hellcat. Commander David McCampbell would later lead Air Group 15 from USS Essex and speak to the tactical effectiveness of the new fighter design as squadrons engaged Japanese aircraft across the Central Pacific. The F6F's superior altitude performance allowed American pilots to dictate engagement terms by attacking from advantageous positions while retaining the option to disengage through diving acceleration that Zero pilots could not match. McCampbell's assessment described the Hellcat as a stable gun platform that enabled accurate fire delivery during high-G maneuvering, while providing pilot protection that ensured survival rates dramatically higher than previous American fighter operations. Japanese tactical doctrine had been optimized for individual combat between highly maneuverable aircraft flown by expertly trained pilots who emphasized aerobatic skill and fighting spirit over systematic gunnery training. The Hellcat's design philosophy reflected fundamentally different priorities that emphasized firepower concentration, pilot protection, and mechanical reliability over pure maneuverability. This design approach proved devastatingly effective against Japanese tactics that relied on turning fights and close-range cannon engagements where pilot skill could overcome equipment disadvantages. Veteran Japanese pilots observing the engagement noted that American fighters were demonstrating performance characteristics that exceeded all previous intelligence estimates. The Hellcats were outclimbing Zeros above medium altitude, maintaining speed advantages throughout the engagement, and delivering firepower that destroyed Japanese aircraft with brief firing passes. Unit commanders radioed that the American fighters appeared to be entirely new designs rather than modifications of familiar types. The Fast Carrier Force's introduction of the F6F Hellcat represented the culmination of systematic American efforts to counter Japanese air superiority through technological advancement rather than tactical adaptation alone. Where earlier American responses to Zero dominance had focused on improved pilot training and modified engagement techniques, the Hellcat provided hardware superiority that enabled less experienced American pilots to engage veteran Japanese aviators with confidence. Even on their first combat missions in F6Fs, U.S. Navy pilots began scoring multiple victories against opponents who had accumulated experience against earlier American fighters. Damage assessment conducted by Japanese intelligence officers revealed the extent to which American fighter design had evolved beyond previous capabilities. Zero pilots reported that 50 caliber rounds from the new American fighters caused immediate catastrophic damage rather than the gradual degradation associated with smaller caliber weapons. The Hellcat's concentrated firepower eliminated the tactical advantage that Japanese pilots had enjoyed when their superior maneuverability allowed them to absorb initial damage while maneuvering for counterattacks. Lieutenant Junior Grade Alex Vrashu, flying an F6F-3 from USS Intrepid, would later demonstrate the Hellcat's capability during the Battle of the Philippine Sea by shooting down 6 Japanese aircraft in 8 minutes during a single engagement. This level of combat effectiveness reflected systematic advantages that the F6F provided over earlier American fighters. The Hellcat's speed and climbing ability allowed pilots to engage Japanese formations before they could achieve tactical positioning, while superior firepower enabled quick kills that prevented prolonged maneuvering combat where Japanese pilot skill might prove decisive. Industrial production capacity demonstrated American technological advantages that extended far beyond individual aircraft performance. Grumman's Bethpage factory would produce 12,275 F6F Hellcats between 1942 and 1945, achieving peak production rates of roughly 1 aircraft per hour during critical periods. This manufacturing capability enabled the U.S. Navy to deploy large numbers of Hellcats simultaneously, creating numerical advantages that compounded the tactical superiority provided by individual aircraft performance. Japanese aircraft production, constrained by material shortages and manufacturing limitations, could not sustain losses at rates imposed by Hellcat effectiveness. Combat results from the Marcus Island engagement provided immediate confirmation of Hellcat superiority over Zero fighters in actual combat conditions. American pilots reported victories against Japanese aircraft that had previously required careful tactical planning and superior positioning to engage successfully. The F6F's performance advantages allowed direct attacks against Zero formations without the complex maneuvering required when flying earlier American fighters. Japanese losses included experienced pilots whose expertise had been accumulated through months of combat against earlier Allied aircraft. Fighter Squadron 5's combat report documented systematic advantages that the F6F provided in air-to-air engagement. The Hellcat's speed allowed American pilots to control engagement timing by attacking when conditions were favorable and disengaging when threatened. Superior climb rate enabled altitude advantages that translated into tactical positioning benefits throughout combat. Most significantly, the F6F's firepower concentration achieved decisive results with brief firing passes that eliminated the sustained maneuvering combat where Japanese pilot skill and aircraft agility provided advantages. Radar-equipped F6F-3 night fighter variants would later extend American technological superiority into nighttime operations where Japanese fighters had limited effective countermeasures. The N/APS-6 radar system installed in about 200 F6F-3 aircraft enabled successful interceptions of Japanese bombers during hours when visual combat was impossible. This capability represented technological advancement that Japanese aircraft could not match at scale, providing Americans with tactical options that effectively expanded operational coverage to continuous 24-hour air superiority. Japanese naval assessments were forced to acknowledge fundamental shifts in air combat effectiveness that favored American technological advantages over pre-war pilot training and aircraft design assumptions. The Zero's initial superiority had been based on performance optimization that sacrificed protection for maneuverability and range. American responses emphasized pilot protection and firepower concentration that proved more effective in large-scale combat operations where individual pilot skill was less decisive than systematic technological advantages. The Battle of the Philippine Sea in June 1944 would demonstrate Hellcat effectiveness on a massive scale during what became known as the Great Marianas Turkey Shoot. Task Force 58's 15 fast carriers deployed approximately 475 F6F Hellcats against Japanese naval aviation's largest remaining concentration of experienced pilots and aircraft. American pilots claimed on the order of several hundred enemy aircraft destroyed, most of them by F6F pilots, while U.S. fighter losses in the air were limited to a few dozen. This lopsided exchange demonstrated systematic technological and doctrinal superiority that Japanese forces could not overcome through tactical innovation or pilot skill. Descriptions of the engagement as resembling an old-time turkey shoot reflected the one-sided nature of combat between technologically superior American fighters and Japanese aircraft that had been optimized for different tactical requirements. Hellcat pilots reported that Japanese aircraft exploded or caught fire when hit by .50 caliber rounds, while their own aircraft absorbed multiple hits from Japanese weapons without losing combat effectiveness. This durability advantage enabled American pilots to press attacks aggressively while maintaining confidence in their ability to survive battle damage. Fighter direction officers coordinated Hellcat interceptions from Task Force 58's combat information centers using radar systems that provided early warning and precision guidance capabilities unmatched by Japanese forces at that stage of the war. American pilots received tactical information that enabled optimal positioning before visual contact with enemy aircraft, while Japanese pilots relied largely on visual reconnaissance and less integrated control. This technological integration demonstrated systematic advantages that extended beyond individual aircraft performance to encompass entire operational systems. Pilots described Hellcat performance advantages in terms that emphasized the aircraft's forgiving characteristics and overwhelming firepower. The F6F enabled aggressive tactics that would have been suicidal in earlier American fighters, while providing protection that ensured pilot survival even when tactical errors resulted in battle damage. This operational confidence translated into combat effectiveness that enabled American pilots to engage Japanese formations without the careful planning required when flying inferior aircraft. Japanese pilot training programs could not adapt quickly enough to counter American technological advantages that had fundamentally altered Pacific air combat requirements. Zero pilots trained in individual aerobatic skills and close-range maneuvering combat found themselves engaging American fighters that controlled engagement terms through superior speed and altitude performance. Traditional Japanese tactics became counterproductive when employed against opponents who could dictate combat conditions through technological superiority rather than pilot skill. Technical intelligence gathered by American forces from captured Japanese aircraft confirmed that Zero design limitations could not be overcome through modification or pilot training. The fundamental design philosophy that emphasized maneuverability over protection and firepower was inadequate for combat against technologically advanced opponents who prioritized pilot survival and weapon effectiveness. Japanese attempts to improve Zero performance through engine upgrades and armament modifications provided marginal improvements that did not address basic structural vulnerabilities. Manufacturing quality differences between American and Japanese aircraft production became increasingly significant as combat intensity accelerated throughout 1943 and 1944. Hellcat fighters incorporated high-grade materials and precision manufacturing techniques that ensured consistent reliability under combat conditions. Japanese aircraft production, affected by material shortages and declining manufacturing standards, produced fighters with reduced operational reliability that affected combat performance and pilot safety. Maintenance and logistics support systems demonstrated additional American advantages that complemented technological superiority in individual aircraft performance. Hellcat fighters were designed for rapid field maintenance using standardized parts and simplified procedures that enabled high operational readiness rates. Japanese maintenance systems, developed for peacetime operations with limited resources, could not sustain the intensive combat operations required by sustained air warfare against technologically superior opponents. Pilot replacement and training programs illustrated systematic differences between American and Japanese approaches to maintaining combat effectiveness. The U.S. Navy's pilot training infrastructure could replace combat losses while simultaneously expanding operational capability, ensuring that Hellcat squadrons maintained experienced leadership while integrating new pilots effectively. Japanese training programs, optimized for producing small numbers of highly skilled pilots, could not sustain the attrition rates imposed by combat against technologically superior American aircraft. Combat air patrol effectiveness demonstrated how Hellcat performance translated into strategic air superiority over contested areas. F6F fighters could maintain continuous coverage over American fleet operations while simultaneously conducting offensive sweeps against Japanese airfields and aircraft. This operational flexibility enabled American forces to protect their own operations while systematically degrading Japanese air capabilities through sustained combat pressure. Fighter sweep operations conducted by Hellcat squadrons systematically destroyed Japanese air power at its sources by attacking aircraft on the ground and engaging defensive fighters under conditions favorable to American technological advantages. F6F performance enabled penetration of Japanese air defenses through speed and altitude capabilities that enemy fighters could not effectively counter. These offensive operations eliminated Japanese aircraft before they could threaten American naval forces or ground operations. Close air support missions demonstrated Hellcat versatility in roles beyond air-to-air combat. F6F-5 variants equipped with wing pylons for bombs and rocket rails provided effective ground attack capabilities, while maintaining air-to-air performance that ensured survival against Japanese fighters. This multi-role capability enabled efficient use of limited carrier deck space, while providing comprehensive air support for amphibious operations. Night fighter operations conducted by radar-equipped F6F-3N and F6F-5N variants extended American technological advantages into periods when Japanese forces had previously enjoyed relative safety from air attack. Hellcat night fighters achieved successful interceptions of Japanese bombers and reconnaissance aircraft during conditions when visual combat was impossible. These capabilities provided continuous air defense coverage that eliminated Japanese tactical options for avoiding American air superiority. Photo reconnaissance missions flown by F6F-3P and F6F-5P variants provided intelligence gathering capabilities that enhanced American operational planning while demonstrating Hellcat survivability in contested airspace. These aircraft could penetrate Japanese air defenses to gather tactical intelligence while retaining combat capability to engage defending fighters. The combination of performance and protection enabled successful completion of reconnaissance missions that provided crucial information for subsequent operations. Training aircraft applications demonstrated Hellcat characteristics that made it ideal for preparing new pilots for Pacific combat operations. The F6F's forgiving handling characteristics and comprehensive protection systems enabled inexperienced pilots to develop combat skills without the high accident rates associated with higher performance fighters. This training efficiency ensured steady replacement of combat losses while maintaining squadron effectiveness throughout intensive operations. Reserve squadron operations extended Hellcat service life well beyond World War II, demonstrating the aircraft's fundamental soundness and continued relevance in post-war naval aviation. F6F-5N night fighters remained in active service into the mid-1950s, providing air defense capabilities that bridged the transition between propeller-driven and jet-powered naval fighters. This operational longevity reflected design quality that exceeded immediate wartime requirements. Combat statistics compiled at the end of Pacific operations confirmed Hellcat effectiveness in quantitative terms that demonstrated clear technological superiority over Japanese aircraft. F6F pilots were credited with destroying over 5,000 enemy aircraft while losing only a few hundred Hellcats in air-to-air combat, achieving an overall kill-to-loss ratio on the order of 19-1. This performance represented the highest combat effectiveness achieved by any World War II naval fighter aircraft and established standards for carrier-based fighter design that influenced subsequent development programs. ACE pilot production statistics illustrated Hellcat effectiveness in enabling individual pilot success against Japanese opposition. The F6F produced over 300 fighter aces, with hundreds of pilots achieving 5 or more confirmed victories while flying Hellcats. This achievement reflected aircraft characteristics that enabled consistent combat success rather than occasional individual victories against superior opponents. Production efficiency demonstrated American industrial advantages that complemented technological superiority in determining Pacific War outcomes. Grumman's ability to produce over 12,000 Hellcats in slightly more than 3 years established manufacturing capabilities that Japanese industry could not match. Peak production rates of approximately 1 aircraft per hour enabled rapid deployment of large Hellcat forces that overwhelmed Japanese air defenses through numerical superiority combined with technological advantages. Operational readiness rates maintained by Hellcat squadrons exceeded those achieved by Japanese units operating Zero fighters under comparable conditions. American maintenance systems and parts availability ensured that higher percentages of available aircraft remained mission-capable throughout intensive combat operations. This reliability advantage multiplied the effectiveness of numerical superiority by ensuring that American technological advantages were consistently available during critical engagements. Strategic impact assessment conducted by post-war analysis confirmed that Hellcat introduction had been decisive in establishing American air superiority over the Pacific theater. The F6F's technological advantages enabled American forces to neutralize Japanese air power systematically, while protecting their own operations from effective air attack. This strategic success provided the foundation for subsequent amphibious operations that achieved victory in the Pacific War. The August 31, 1943 engagement over Marcus Island represented a visible turning point as U.S. carrier raids carried the war westward with new tools. Toshiyuki Sueda's destruction by Richard Losch's Hellcat demonstrated technological superiority that would characterize American fighter operations for the remainder of World War II. Japanese air power, which had dominated Pacific skies in the early phases of the war, was systematically dismantled by American technological advancement that prioritized pilot protection and firepower effectiveness over the maneuverability and range optimization that had characterized Japanese fighter design. From Marcus Island through the Great Marianas Turkey Shoot to the final air battles over Japan itself, the F6F Hellcat established American technological superiority that Japanese forces could not overcome through tactical innovation or pilot skill. The transition from Japanese air dominance to American air supremacy was achieved through systematic application of superior technology that outclimbed, outpaced, outgunned, and outlasted the Zero fighters that had once seemed invincible. The stubby Grumman fighter that had emerged from Long Island factories in 1943 had fundamentally altered the balance of Pacific air power, ensuring that Japan would never again achieve the air superiority that had characterized the early phases of the Pacific War.